paper, we have compared the iterative methods of root finding with comments on reliability of convergence. To understand this question better, we will make a table of iterative methods with their different conditions and different reliability of convergence. We have 5 iterative methods, and that are bisection, false position, Newton-Raphson secant method, and the successive approximation method. In each method, we have different iterative formulas, and the order of convergence is obviously different for each method, which gives us different results at different times. So let's start with the first method, which is bisection method, which has an iterative formula for m, that is root, is equal to a plus b by 2, where the root is always between a and b, which is a closed, which is in a closed brackets, a and b. The root is between a and b, and the order of convergence for this bisection method is gain of 1 bit per iteration. It means every iteration breaks closer to our root of the equation. Evaluation of functions per iteration. In each iteration, we have to iterate one function. We have to solve one function, as you can see here, which is a plus b by 2, only one function. And the reliability of convergence is guaranteed convergence. What does this guaranteed convergence means? This means it is the simplest iterative method and is guaranteed to converge. Convergence is slow and steady in bisection method. The second method is false position method, which uses the iterative formula as m is equal to a of f of b minus b of f of a upon f of b minus f of a. Again, the root is between a and b, and the number of functions we are using in this formula again is only one. As you can see, this f of a and f of b is only one function with two different values, that is again 1. And the order of convergence for false position method is 1. It is slow as it is the first order convergent method. The amount of computational effort per iteration is one function evaluation. And the convergence is guaranteed here. It is not necessarily monotonic convergence to the root, but most often it will be superior to bisection method. False position method is most of the time is superior to bisection method. The third iterative method is Newton-Raphson method, which uses the formula m is equal to b minus f of b upon f dash b. The order of convergence of Newton-Raphson method is 2, and the number of functions per iteration evaluated are also 2. As you can see here, its first one is f of b and the other one is f dash b, which will be another function, but the derivative of the function we used before. The convergence is fast if point is near the root. That is, if b is near the root, we have taken the value of b is near the root, then the convergence will be fast. In Newton-Raphson method, it has the fastest convergence. It is an excellent method if 1 is near the root. It is, however, quite sensitive as it diverges if f of x is near 0 anytime during the iterative cycle. Besides, this amount of computational effort required in computing the values of f of b and f dash b is considerable, and the overall computing time may be large in spite of the inherently higher rate of convergence. The next method is secant method, which is very similar, which has the same formula with the false position method and is very similar to the false position method. The only difference is that the root may not be between a and b. A and b can have any values. It shouldn't have any closed interval. We can take any a and b, whereas the order of convergence for secant method is 1.6180, and the evaluation per iteration is again same as false position method. We are using the same function f of a for f of a and for f of b. but here the reliability of convergence is non-guaranteed. Secant method has a non-guaranteed convergence, but if converges, it converges faster than the false position method. The last iterative method is successive approximation method. In this successive approximation method, from f of x, we find a function g of x that will help us find the root of f of x easily. The order of convergence of successive approximation is 1, and the number of functions per iteration evaluated is also 1. We can see here we have two functions, f of x and g of x, but we will not use f of x here. We will evaluate the roots on the basis of g of x that we have found from f of x. Make sure you use successive approximation method only when you get g of x correctly. This method is suitable for only some special cases and is again first order convergent but has no guaranteed convergence.